All right, so one of the things that we've been doing so far is looking at operators. An operator is quite powerful, the Heaviside operator. But there's an interesting aspect, historical aspect to this thing, which has made it work the way it has, which is the fact that Oliver Heaviside was a very interesting character. He was an engineer, really. I mean, but he developed all these mathematical techniques, and actually he was the one who applied this operator method to solving equations and solving circuit problems and so on. But he was not a classic mathematician in the sense that he wouldn't prove things, he wouldn't think that it's necessary to prove things. So what happened is that he got into these fights with people who were in the business of proving things, sometimes useless things, but nonetheless just they were in that business. So he got into a fight with these people, and eventually some of these people said, okay, wait a second, it seems that this is working, so they went and tried to prove it, and the way they proved this background of these things was using complex complex calculations and complex integrals and improper integrals. And eventually what it turned out is that it's some variation of something that Laplace had done at some point in their life, and they called it Laplace transform. Now, Laplace transform is actually a lot less general. I mean, it's less general than the Heaviside approach because it relies on improper integrals and convergence of improper integrals. So, but because everybody hated Oliver Heaviside, everyone switched to Laplace transform. They couldn't bring themselves to use his method, although it was a very good method. So the lesson in that is that, if you come up with good method, it's also helpful to be nice to people. Or even if you don't come up with good method, particularly if you don't come up with good method, it's even more important to be nice to people. So anyway, but everything essentially, most of the textbooks are written in terms of Laplace transform. A lot of things are done in Laplace transform. So it's important for you to be familiar with that language. So we'll spend this part of the lecture, this 1 hour or less, on Laplace transform. And you will see, essentially, it's the same machinery. It's very similar, but we'll see how it comes about. So let's do it quickly. So one of the things that we did last time is that we said if you had a system with an impulse response of h of t, and if you look at its response to an input x of t, which is e to the st, right? So if you just have e to the st as the input, no u of t, so this is a two-sided input. But h of t could be one-sided, and if it's a causal system, then it will be one-sided. So how do you determine the output, y of t? Y of t is determined by the convolution of x of t and h of t, which is by definition the integral from negative infinity to positive infinity of x of, so basically h of t tau, x of t minus tau d tau, which you can write using that input, particular input. You get it as from negative to infinity to positive infinity of h of tau, e to the st, e to the negative s tau d tau. And you can see that this is not a function of tau, so you can actually bring it outside the integral, and this is what you're left with. Now, this part, which takes its function, a time domain function, h of t, and produces a function of s, where s is a complex quantity, is called the Laplace transform. It's a two-sided Laplace transform. So you show it with Laplace transform of h of t, which is basically capital H of s. And it's the weight of this function, e to the st. Now, if you have a one-sided input, if you have, for example, in other words, if your system is causal, what does that mean? It means that it can't produce an output before it has an input. Which, if you think about it, in an impulse response language, it means that its impulse response has to be 0 for t smaller than 0. Right? So if you have a causal system, it means that h of t is 0 for t smaller than 0. In that case, what you end up with is the so-called one-sided Laplace transform, which is basically just a two-sided Laplace transform applied to a causal system, which would basically change this integral from negative 2 plus infinity of h of tau e to the s tau d tau, negative s tau. So this becomes your Laplace transform in that case, if you have a causal system. So you don't need to calculate it from negative infinity to plus infinity. You will need to calculate it from 0 negative to plus infinity. So they are the same thing. There's a lot of books and all those things that make a big deal about one-sided Laplace transform or two-sided Laplace transform. It's really the same thing. If your function is one-sided, then this integral is calculated this way. And the reason you pick 0 negative here is that there may be interesting things happening at 0. So this allows you to deal with those. For example, an impulse. If you have an impulse, that impulse, does it fall inside the, do you need to calculate it within this integral or not with this limit? Yes. So all of those are captured. The things that happen exactly at 0. That's why you go from 0 negative. And that's why you make that distinction, because I want to capture all the interesting things that happen at 0 too. It's right before all the exciting things happen. Okay. So that's the definition of Laplace transform. I mean, that's what it is. So now it has certain properties. We can go over the properties quickly. So I'm going to go over some, essentially kind of a laundry list of properties. And then we'll see how they can be useful. And you will see that you already know pretty much most of them because of the way we've dealt with the operators. So for example, the first question is, so let's say some of the basic properties. So let's say if you have a different, what is the Laplace transform of the derivative of a function? I'll show it as p x of t. So what is it? How do we calculate it? Well, we can go back to the definition. So this is, if you know the Laplace transform of a function itself, what is the Laplace transform of its derivative? How do we do that? Well, we apply the definition. So this is dx dt e to the negative st dt. Right? So how do we deal with an integral like that? You integrate by part, right? So how do we integrate by part for something like this? So this can become your du, and this is the s. So basically you get x times what? So what's the first term in this integration? So what are v and u in an integration by part? X and e to the negative st, right? So it's x of t e to the negative st. And then how about the other side? So this is from negative infinity to plus infinity minus what? Then you get integral of x e to the negative st dt. You have to calculate the derivative of this thing, which gives you a negative s, so you get an s up front. Right? If this is v, this is u, du is going to be negative s in e to the negative st dt. Right? So this part is clear how you deal. And what is this? So this is from negative infinity to plus infinity. What is this? You should recognize this now. This is the Laplace transform of x. You can show that capital X of s. So how about this part? Well, in general, if you don't know anything about x of t, this is not going to be easy to calculate or converge necessarily. But if I tell you that x is one-sided, x of t is one-sided. So for one-sided x, in other words, x of t is 0 for t smaller than 0, what is this going to be? That is going to be x of 0, right? So what you're going to get is that for this term you get a 0 for plus infinity, because this goes to 0, as long as this is finite at infinity. And this doesn't matter except for from 0 minus to that point. So this is going to be negative x of 0 minus. So this is going to be evaluated at 0 minus. So you can actually say 0 minus, and then this is x of 0 minus and e to the 0 minus, which basically gives you 1. So the whole thing becomes s times x of s from this term minus x, lowercase x, of 0 minus. All right. So that's what it is. So now the first term should be kind of like, you can see that it looks kind of like a px, right? Sx. And the second term is also somewhat similar to what we had. You remember when we were dealing with the initial conditions under Heaviside operator? You remember we had these terms, these additional terms, like y of 0 and y prime of 0 and things of that sort, those initial conditions. So this is exactly the same thing. So that's what it is. Now, if you don't have any initial conditions, so this would be if x of 0 minus is 0, then this becomes just simply s times capital X of s, which is the Laplace transform, which basically is saying it's called the zero state Laplace transform, where you have no initial condition. Now, and from that, you can easily see that Laplace transform of 1 over p of x of t is going to be x of s over s. It's the inverse of that. What is the Laplace transform of a function e to the negative at times x of t? So if you have a function, if you know the Laplace transform of this, and if I wanted to express the Laplace transform of a function that has an e to the negative at times that, how would I do that? Again, plug it into the definition. So this basically becomes negative integral from negative infinity to plus infinity of e to the negative at e x of t e to the negative st dt. So these two you can combine clearly, and then this becomes negative integral from negative infinity to plus infinity of x of t e to the negative s plus a t dt. So how can I write this in terms of its Laplace transform? If capital X of s is the Laplace transform of x of t, what is this function? How can you write this? Isn't it simply x of s plus a by definition of Laplace transform? Right? So that's what it is. So an exponential multiplication by an exponential in time corresponds to a shift in the Laplace domain by a, which is the negative of that coefficient. Okay, so that's one set of properties. Now the other question is, what is the Laplace transform of some of the elementary functions we've been dealing with? So again, you will see these are all becoming should be pretty straightforward at this point. So what is the Laplace transform of the Dirac delta? One. Why? Okay, let's see. That is correct. 1 is correct. And so what is it? It's delta of t e to the negative st dt. So delta of t is non-zero only at t equals 0, right? So this function only, the value of this function only matters at t equals 0. So this exponential is 1. And therefore, it's an integral from negative infinity to positive infinity of delta of t dt, which is 1 by definition of delta. So you can see, you remember you remember that operator catalog that we talked about? What was the entry item for delta? What was the operator associated with delta? 1, right? So it shouldn't be surprising at all, because this is the response of the system calculated to the e to the st, right? So what is the Laplace transform of u of t? Take a guess. 1 over, there's no p. 1 over s, yeah. So let's see if that's the case. So how do we do it? Let's do it directly from the definition, right? U of t e to the negative st dt. So this is basically the same integral from 0 to infinity of e to the st dt. What is this integral? It's negative 1 over s integral. So it's negative 1 over s e to the negative st evaluated from 0 to infinity, which The infinity gives you 0 minus this for 0, which is 1, so it gives you 1 over s. You remember the 1 over p? That's 1 over s. So what is the Laplace transform of e to the negative at u of t? What do you expect it to be from what you already know? 1 over s plus a, right? So let's see if it's true. Negative infinity plus infinity, e to the u of t up front, e to the negative at, e to the negative st dt. You can combine these. So the u of t gives me, just changes the limits of integration. So it gives you from 0 to infinity. This becomes e to the negative s plus a t dt. And similar to that integral, this becomes 1 over s plus a. In fact, did I even need to do this calculation knowing this property and this result? Right? It's the same thing. So if this is x of s, all I needed to do when I had an exponential in front, I had to calculate x of s plus a. In other words, I replace s with s plus a, which is this. So you can see that we can arrive at this like multiple ways, which should make it more intuitive in your mind. Now, the Laplace transform of, similarly, you can show that the Laplace transform of t to the m over m factorial u of t. You can do it as a succession, right, of derivatives. So you can actually show it as Laplace transform of 1 over p to the m. You can make it off of this, right? And integrating it m times produces that. And when you do that, it's basically this, you are using this property multiple times. Right? So for every one of those integration that you have, you get a 1 over s. So overall, you get 1 over s to the power of m, which is very, I'm sorry, s plus m plus 1. Because u of t also kind of like generates one s itself, right? One of the s's comes from this guy itself. Because, remember, all of these things are generated off of an impulse. So you need an extra 1 over p. Like if I could write this as 1 over p plus m plus 1, or 1 over p to the m plus 1 of delta of t. Right? That would have been the way to do it. And delta of t gives you 1. So these two are the same. Because to get a u of t off of a delta, you need an integrated ones. Make sense? So if I tell you this and I ask you what is the Laplace transform of t to the m over m factorial e to the negative at u of t, what can you tell me from what we already know? You should be able to derive it very quickly from this and that property. And this property. So what is it going to be? When you know this result and you know that property, so what is it going to be? 1 over s plus a to the power of m plus 1. So you can solve differential equations exactly the same way, essentially. Yes? So how do you generate this function off of u of t? If you integrate it m times. I'm doing just time domain. Okay. I'm not worried about the Laplace transform in this step. I just took this function and wrote it in this form. This is the mth integral of u of t, right? Because the first integral gives you t u of t. The second integral gives you t squared over 2 factorial u of t. The third one gives you t cubed over 3 factorial u of t. so on and so on. Every time you integrate it, you go 1t up, and then you also add that power to the denominator to account for the derivative, the coefficient of the derivative, right? Yes?
How does this generalize past the input being e to the st?
How does it generalize past that?
Yeah.
You mean for other functions, you mean? Yeah, so there's a set of different functions. You can try to say basically, it generalizes to the extent that you can always calculate this integral, right? I mean, or the definition integral, right? So if you can evaluate this integral, which I didn't even box, because I think it was a trivial conclusion of what we have already said. If you can evaluate this integral for a time domain function, it would produce a function of a complex function of S, right? So for certain things, you have closed form analytical solutions. For certain things, you don't. And you will see it's pretty much the same things that you have elements in the catalog for. But they're also useful for. Now, the only advantage of it, if you will, is that you don't really need to think. So it's a little bit more elementary in the sense that you don't need to think about an operator. It takes a function, and off of a function, it takes the function and then produces another function. It is an operator itself, right? But you don't need to think about it. So, well, this is just a transform. This is the Laplace transform of that. And you can deal with Laplace transforms directly. So, for example, let's just do an equation, or like an example of a differential equation. So let's say you have y double prime plus 3y prime plus 2. Y is x, and let's say x is, I don't know, what did I choose here? That doesn't matter. You can pick whatever. E to the negative t u of t. Right? So what I can do, I can directly do a Laplace transform of both sides. Which again, I could have done with the operator as well. But so take a Laplace transform of the left-hand side. What do I get? If there's no initial condition, there's zero state, what do I get for this part? I get y of s times s squared plus 3s y of s, right? It's two derivatives, right? S squared. And then plus 2y of s. And I take the Laplace transform of the right-hand side. What is the Laplace transform of this? It's 1 over s plus 1, right? So now if I want to solve this, I can factor the characteristic polynomial and divide both sides by that. So I get s plus 1 times s squared plus 3s plus 2, which can further be factored by 1 over s plus 1 squared 1 over s plus 2. So if I want to find the response of this thing, I have to do a partial fraction expansion of this, which is 1 over s plus 2, 1 over s plus 1 squared, well, 1 over s plus 1. So the coefficient for that is multiplied by this, eliminate that, set s to negative 2. What do I get? I get 1. Multiply by that, set s to negative 1. I get 1. And take whatever is left, okay, and take a derivative of that. Right? What do I get? Right, so I get the derivative of that is basically the derivative of the numerator divided by times the denominator minus that. So it's basically just a 2. So 1, negative 1 over, so it's negative 1 divided by s plus 2 squared for s equals negative 1. So it's basically 1 is a negative 1. So, and then the way you do inverse essentially is the same thing. You need the catalog. So it's no stronger than that as a transform. And I will tell you why this statement is important in a second. So then you want to see what's y of t. You basically say it's basically e to the negative 2t u of t for each one of them, plus t e to the negative t u of t minus e to the negative t u of t. So I mean, you can see there's nothing new here in the sense it's very similar to what we did with the operator fundamentally, but it's something to be familiar with. Now, also, there are some other properties of Laplace transform I'm going to go over again to make sure that we cover everything. There are a couple of interesting things about it, but one aspect of Laplace transform, which you should keep in mind, is that this Laplace transform, to invert it, there's no closed form thing, at least in our domain. I mean, there's one in a complex domain, but it's a total mess and it's not easy to calculate. So the advantage of a transform over an operator, for it to be really useful, if it's a useful transform, is that its inverse is easy to calculate. And the inverse of Laplace transform is not easy to calculate. It is something that's complex, and it's just you have to use a catalog. If you have catalog entries like that, if you have rational functions, then you can do it easily because you have all these things. There's some other functions for which you can tell what it is, but other than that, it's difficult. Now, you will see that when we go to Fourier transform, which is a special case of Laplace transform. So you remember, Laplace transform was actually essentially a special case of the operator. And Fourier transform is a special case of Laplace transform. You know how it's a special case of that? It's calculated for S being j omega. When S is purely imaginary, not just a complex number, then it has a very inverse that's easily calculated. In fact, we can show it's that its inverse it's itself with a minus sign. Can you think of an operator that's its own inverse? They're simple algebraic ones. If you have some Gaussian, yeah, Gaussian, simpler ones, even simpler. Negative, yeah, multiplying by minus, inverting the sign, right? You invert it twice, you're back to the same thing. And you see Fourier transform is extremely useful because of that inverse. And you will see that Fourier transform is like 20-30% of engineering is Fourier transform, right? So when we get to talk about it, it's just you will see, and it has many, many implications because that inverse is easy to calculate, and more importantly, is easy to visualize. It's possible to visualize, at least for me. I'm not sure how I can visualize the inverse of a complex. Maybe some people can. I can't. Some complex integral. Okay. So that's what. But so let's do a few more properties of the Laplace transform, and I'm going to take you over a catalog. Any questions about this so far? So I'm just going to take you through the catalog of these properties, and we'll take it from there. So, let's see. Now, Laplace transform, by definition, well, from the definition, you can see that the Laplace transform is linear. So it has one interesting property, which is a linearity. So the Laplace transform of a1 f1 of t plus a2 f2 of t is equal to a1 Laplace transform of f1 of t plus a2 Laplace transform of f2 of t, which usually show with capital letters, a1 capital letter f1 of s plus a2 f2 of s. So it's linear. Now, this is a useful property because if you, for example, want to calculate certain Laplace transforms, you can use this to calculate them as one way to calculate them. There are many different ways. So let's say you have cosine of omega t u of t. What's the Laplace transform of that? Well, you can directly try to calculate that integral, and you can do it. But there's an easier way. You can write this as a linear sum of two things. What are those two things? Cosine, you can write it as sum of two things, which are the exponentials, right? So you can write it as e to the j omega t plus e to the negative j omega t divided by 2 u of t. So you apply the Laplace transform to those two individually. You get e to the j omega t u of t plus 1/2 Laplace transform of e to the negative j omega t u of t. So what do we have? What is the Laplace transform of this thing? Have you already calculated this? On that other whiteboard? It's e to the negative at, right? So what is it going to be? 1/2 of 1 over s plus or minus? Minus j omega plus 1/2. The other one is 1/2 1 over s plus j omega. So what is that sum? That sum is 1/2. So what's the common denominator? Is the product of the two. They're complex conjugates of each other. So you get s squared plus omega squared. Then you get this plus that. So the s's add and the j omegas cancel. So that you get two s's, which hence cancels the 1/2. So you get s over s squared plus omega 0 squared. Which again shouldn't look that surprising. Okay. Now another property, scaling property. In other words, what's the Laplace transform of a function of a scaled input, f of at? So it's the integral, by definition, from negative infinity to positive infinity of f of at e to the negative st dt. So how do you deal with that? Well, you need a change of variables, right? You can define this as, I don't know, tau. Tau is at. So you need a change of variables. So it would be, again, integral from negative infinity to positive infinity, because a times infinity is still infinity. Now, and then it becomes f of tau. This becomes e to the negative s over a tau, because t is tau over a. And then the differential becomes d tau over a. So you can factor the 1 over a out, and what is left, what is this? Can you write it in terms of, so I want you to stop writing for a second and tell me, if I take the 1 over a out, this thing that's left, can you express it in terms of capital F of s with a different argument? It's f of s over a, right? So it's f of s over a. So that's the scaling property. When you scale the argument, the function, the Laplace transform scales that way. So there are other properties, right, for Laplace transform. Time shift. Let's say you time shift your input. What happens? So let's say if I time shift an input, so let's say if it's a function f of t, u of t, then it becomes f of t minus tau, u of t minus tau. What's the impact of the time shift on the Laplace transform? So again, we plug it into the definition. So it's the integral from negative infinity to positive infinity of f of t minus tau, u of t minus tau, e to the negative st dt. Now, the u of t minus tau does something, right? Is 0 for certain t's. So it basically is not, it's 1 for what values of t? T's greater than tau. So this limit of integral can change from negative infinity to tau to plus infinity, and you can get rid of the u of t. So you get f of t minus tau e to the negative st dt. So I do a change of variable. I call this tau prime, t minus tau, right? So if I do that, then the limit of integral goes back to 0. So it becomes f of tau prime. Then this becomes e to the negative st, s tau prime, e to the negative tau, s tau. And then I get a d tau prime, right? And then what happens is that I get this, and then this can be factored because it's not a function of tau prime. So you get e to the negative s tau, or tau prime s. That's a better way of writing it. tau prime s. And then what is left is the Laplace transform of f of tau u of t, f of t u of t, because if I put the u of t in there, nothing will happen. I can put the u of t up front, and I can write this as f of t, Laplace transform of f of t u of t. So you can see what happens is basically that the Laplace transform of the time-shifted signal is the Laplace transform of the original signal times e to the negative s tau s. You remember what it was for the operator? It was e to the negative tau p. So essentially all the p's are becoming s's. That's what's happening. And that's why I sound a little bit less excited about this development as I'm telling you. So, yeah, it's this. Because we already have done the hard work. So now we can. There are essentially these properties that we have. So there are a couple more that I think are worth knowing about. Which we'll go over quickly now. So these are called the initial and final value theorems or properties. So initial value property. So what this does is basically you can if you calculate the Laplace transform of dx dt, right? What we already have done, we calculated this earlier, it's on the other whiteboard, is going to be Laplace transform of the derivative is going to be sx of s, capital X of s, minus lowercase x of 0 minus, or 0 for now. So if you're interested in determining what the value of a function is, we are doing this. But now, think about this. What is the value of this for s going to infinity? If I evaluate this for s going to infinity, what do I get? Well, on this side, I get whatever this is when s goes to infinity. But on the other side, what happens to the actual integral? So I'm interested in the definition. Well, it's a derivative, so it's dx dt. So what is this function? What is this thing when x goes to infinity? What happens to this term? S goes to infinity, sorry. Goes to 0. So this becomes 0. Which means that the limit of this for s going to infinity is equal to the limit of this going to s infinity. But the limit of this going to s infinity is itself because it has no s dependence. So what it tells you is that x of 0 is equal to the limit of s going to infinity of s times x of s. So this is a way of calculating, if you know something's Laplace transform, you can calculate the initial condition by evaluating this limit. Right? Let me give you an example. So think about x of t being cosine of, e to the negative 2t cosine of 10t u of t, right? So the Laplace transform of this thing, again, from the properties that we calculated before, is s plus 2 over s plus 2 squared plus 10 squared. Right? So now the question is, what is the limit of s times that? So it's s times s plus 2 in the numerator, and in the denominator you have s plus 2 squared plus 10 squared. Limit of this when s goes to infinity. So how do I calculate this limit? Do you know what this limit is? It's a pretty straightforward limit. What is it? It's 1, right? Why? Because when s goes to infinity, the term with the highest power of s in the numerator and denominator matter. If they were of different orders, then you either get 0 or infinity. If they're of the same order, you have an s squared here and s squared here. So they have the same coefficient, so it's the ratio of those two, which is 1. So this is 1. So let's see if it's true. What is this initial? What is the value of this function at t equals 0? This becomes 1. This becomes 1. Right? Now there's an I guess the dual to this, which is the the final value. Final value property, which is kind of like essentially the dual of this. So you basically do the same thing as this, but now you calculate the limit of s going to 0 of the Laplace transform, which basically says the limit of s x of s minus x of 0 minus. Now you do it from 0 minus this time. This is from 0 actually. So this is from 0 minus. Now if you do it from 0 minus, what you have is essentially the integral from 0 to infinity of dx over dt e to the st when s goes to 0 dt. So when s goes to 0, this becomes 1. And this essentially is x of infinity minus x of 0. Right? Or 0 minus, if you do 0 minus. So this is the expression you get, right? Because this dt cancels dt, you're integrating dx from 0 to infinity, and that's what you'll get. So, but look at the both sides of this equation. So the limit of this side is essentially limit of s going to 0 of s x of s minus the limit of this thing is itself, x of 0 or 0 minus, and then you get x of infinity minus x of 0 minus. So you can see that these two are common. You can cancel them from both sides. So you end up with x lowercase x of infinity, the final value of the function, is the limit of s going to 0 of s times x of s, capital X of s. So it says its final value is this. So let's see if it's true. Again, it's the same product. Now the limit of this thing in this example, if you wanted to look at this example, it's the same product, but now we have to calculate this limit for s equals 0. What is this limit as s equals 0? What does this reduce to at s equals 0? So what is the limit of s going to 0 of s times s plus 2 divided by s plus 2 squared plus 10 squared? What is this limit? 0, right? Because there's an s here, and there's a 10 squared here, and there's some other things here too. So you have a non-zero denominator, you have a 0 numerator, it's 0. So this is going s to 0, sorry, yeah. Which basically means that it's at infinity, the final value of this thing, meaning, so this is equal, the first one was x of 0, and this is x of infinity. So this is equal to x of infinity. At infinite time, this goes to 0, which is true because this is a cosine, but this is a decaying exponential. So eventually this goes to 0, forces everything to be 0. Make sense? All right. Last but not least, convolution. So, how about the convolution of two functions? What if y of t is x of t convolved with h of t? What is the Laplace transform of the convolution of two functions? You can probably guess what it is, right? What is your guess? Yeah, the product of the two Laplace transforms, right? So, but let's see if it's true. So by definition, we can write this as integral from negative infinity to plus infinity of x of tau, h of t minus tau, d tau, right? So then we have to calculate the definition of Laplace transform of that. So y of s, which is the Laplace transform of y of t, is the Laplace transform of that. Which is, we write the definition of Laplace transform, which is integral from negative infinity to positive infinity of e to the negative st dt integral negative infinity to positive infinity of d tau x of tau h of t minus tau. So by the way, when this is a good habit to, when you're doing multiple integrals, they're nested, I'll keep the differential right next to the associated integral. Looks a little bit different, but this way you don't have to say, well, which differential was for which integral. So if you just keep them close to each other, that's fine. It's a product anyway, right? So it doesn't matter if you put it at the end or beginning. Although notation often wants to do it this way. But so what do we do with this? Is there anything we can do about it? Well, I can change the order of the integration. So I can basically just do the integration of negative infinity to positive infinity of d tau and take the stuff that are not functions of t out. So I'm left with an x of t here that I can take out with this d tau. And then we can put this integral inside the other one. E to the negative st h of t minus tau. Right? So this is the time shift essentially, right? What I need, so I want to evaluate this first. To evaluate this, I need a change of variables. I can make this tau prime. Right? If I make that tau prime, what is this new thing going to be? So this is going to be a negative d tau prime. This is going to be e to the negative st. And I can write that as integral from negative infinity to positive infinity of x of tau, well, d tau, x of tau. And then what is left is basically e to the negative tau s h of s. I'm using basically the time delay property. I'm using time shift property. I'm using this, if you think about it. Which is just basically a change of variable, the same change of variable I did. So if I do that, then I'm left with this thing. But now this guy is not a function of tau. So I can take it out of my integral. So it becomes h of s times the integral from negative infinity to positive infinity of x of tau e to the negative s tau d tau. Do you recognize this? Which is, what is that? It's x of s. So it's x of s times h of s. So the convolution, so the time domain convolution translates to multiplication in the Laplace domain as well. And later on, you will see that the same thing is true about Fourier transform, which should not be surprising because it's a special case of Laplace transform. So a time domain multiplication, a time domain convolution corresponds to a frequency domain multiplication. So if you, and this is the transfer function that we calculated. This is the exact same transfer function. This is the Laplace transform of the input, and this is the Laplace transform of the output. So you can calculate the response of the system using the Laplace transform that way as well. Okay. Any questions? Yes, Daniel.
How is this different from what we've been doing?
How is this different from what we've been doing? Well, technically, it's different because you're doing a transformation. You're dealing with a function. You're taking a function from one domain and converting it to another domain. practically, since it's based on the same thing, the machinery looks very similar. And the operation is very similar. But it's not fundamentally different. Not fundamentally. So it's essentially the same thing. And that's why we spend like half a lecture on it and no more. But it's important to know and realize that when you see Laplace transform, it's something that you already know. You just need to know the connection. Right? Any other questions? Yes?
What does the S represent?
S is just a complex number. The same thing as t, where t is a real number, right? It's a parameter. S is a complex parameter. But it's a complex frequency. You can think about it as a complex frequency. All right, see you next time.